have some kind of digital asset that is scarce. And for that to work, we need a blockchain to scale. And that's the first presentation I'm going to have. We're going to have 3 presentations today. I'll introduce Felipe, who is coming from Cal. He's a researcher on decentralized data mining applications. I'm very passionate about things like personal privacy and just you being in control of the data you own. And Larry Salibra, he's working on very exciting identity systems on blockchain. So systems that allow you to maintain a digital identity that is not easily forgeable and that is not, that just creates a kind of like, that creates your identity online in a way that we actually haven't seen it before. And he's going to present Blockstack. So how do I use this thing? Do I control it from?
I'll control it for you.
Oh yeah, beautiful. So I'm throwing myself in there. We have limited ourselves to 20 minutes each, so that in an hour we still have some time to answer questions and mingle a little bit, and maybe even get to know each other. Because I think we're quite a unique crowd in that this is a very still very young kind of technology. Yeah, let's start with the first argument. When Bitcoin transactions are being broadcasted to this entire network, and they're being picked up by miners, they're being picked up by nodes. Each roughly 10 minutes, one of these miners is being arbitrarily chosen, and there are many different ways in which you can arbitrarily choose a miner to decide once and for all which transactions happen in those last 10 minutes. And in Bitcoin, that is called Bitcoin mining, and the way that a node is randomly chosen is by proving that it has wasted a certain amount of energy. The more energy you have wasted in those 10 minutes, the more likely you're going to be chosen. And that makes it very difficult to create multiple identities at the same time, because you need to waste more electricity in order to gain more likelihood. And what you really release when you're being chosen is you release a block like this. And I'm going to first look a little bit of how that block looks up here on the right. That's very technical. It's not necessary that you all remember this. But it's interesting to just think about how big is such a block and how much data is in there. Very beautiful in the beginning. There's something called the magic number, which is just used for software to identify that this is a Bitcoin block. This is also how it's very easy to just fork the Bitcoin network by simply forking that magic number, because soon just by changing that number, a different a Bitcoin node would no longer accept your blocks. It's kind of the easiest way you can do to create an altcoin. It's exactly the same, except that it has a different magic number. The second is the block size. So in the very beginning, the block already reveals this is how big I am. This is how much load I'm going to carry on your network and on your computer. We have, and then comes the block header, which goes more into detail about what information is in there. It reveals a version number. It reveals the hash to the previous block, so it points that I'm following this block. It has the hash of the Merkle root, which contains sort of proof of all these transactions that exist in there. A timestamp in Unix time. The bits, which relate to, also not very interesting for this talk, it relates to the difficulty. The nonce, which is just basically that's your winning ticket. That's the number that you have successfully guessed, which solves this mathematical puzzle, that it makes you being the chosen one for the next 10 minutes. The number of transactions, and you can see that's actually quite slim, but each transaction then contains inputs and it contains outputs. And that's why we cannot really say a transaction is exactly 200 byte large, because a transaction might be 1 kilobyte large, or it might be the largest transaction that happened so far was 1 megabyte large. It just depends on how many inputs does it have and how many outputs does it have. That's also what we cannot really say. This is how many transactions Bitcoin can sustain, because it completely depends on the type of transactions that we see. If you have maybe a Bitcoin block might only contain 1 Bitcoin transaction, or maybe it's going to contain 2,000 or 3,000, 4,000 transactions. But what is interesting for this talk is the statistics. It's the sort of, what does the block that is being released today look like? And we know that it comes roughly every 10 minutes. And then of course it's a very long tail. So it might come after a few seconds, it might come after 10 minutes, but it might only really take a few hours, which means that the average time that it comes is actually a lot larger than 10 minutes. But that's just the way this distribution works. The average right now is, it doesn't sound really full, right? It just sounds half full. But again, if you imagine that there's also a short tail in this case, where you have still quite a few blocks that are completely empty. So if you have during a 5-hour period an average of about 0.8 megabyte per block, then you can really say these blocks are full. Because then that's going to mean that 80% of the blocks are completely full. They have this maximum of 1 megabyte per block. But maybe 20% of them are completely empty. That's just the way a lot of the mining works. If you mine, you want to be able to release it as quickly as possible. Sometimes, especially if you very quickly find a solution, you will reveal your block without any transactions in it. Because creating that merge root also takes a little bit of time. We see right now about 1,000 transactions per block. So that's about 100 transactions per minute. That gives you an idea of how much Bitcoin is, the kind of load that exists on Bitcoin right now. The reward is very important if you think about Bitcoin scaling in the long run, because that reward is going to drop to just 12.5 Bitcoin in about May or June or July next year, which means that a lot of the Bitcoin mining powers at the current rate are not going to be able to sustain themselves. They are right now wasting, for each block, they're wasting roughly 25 Bitcoins worth of electricity. They're mining on the margin. And if they're suddenly only receiving 12.5 Bitcoins, then they're going to have to shut down their miners. And the only way that this system can then scale or maintain this hashing power is for Bitcoin to be worth double as much, or for these transaction fees to compensate for the loss in reward. So we either, in the long run, need Bitcoin to become very valuable to be able to keep this system running, or we're going to need to see these fees going up a lot. And again, with those fees, there's two ways this could unfold. You could see each transaction becoming very expensive, so that these 1,000 transactions, which right now only yield about 0.3 Bitcoin, these 1,000 transactions might actually cost, well, maybe 3 Bitcoin, or maybe even 10 Bitcoin, which would make a transaction very expensive, and suddenly a transaction is no longer cheaper than if you make it with Swift. Propagation time is also very interesting. That's the time that it takes for, this is about, I think, 90% of the Bitcoin network to hear about your block. Of course, there's again a long tail of the distribution. The last node might really only find out about your block after a minute or 2 minutes. And we're definitely approaching the Bitcoin limit. That's sort of the main takeaway from what we learned about this block. So the way that this works right now is, you know how small Bitcoin is, right? We know that Bitcoin is being used, it is establishing itself in certain niches, but it is by far not initiating the kind of revolution that people say it is. It's also by far not threatening banks, or it's by far not threatening companies like Alipay, which are at the peak on November 11 processed 80,000 transactions per second, which of course is just the peak, right? But it's a very impressive number. So that's to next slide, which is just an anecdote. The way this limitation, the way that we're approaching the Bitcoin as a limitation, it's a very artificial limitation. It's not the kind of limitation where we're just investing all sorts of capacities into making it larger and finding a technological limit, but we're just approaching this limit here. I think it was here, max block size equals here. That's 1 megabyte. This was put in by Satoshi Nakamoto himself, I think July 10th, 2010. And that was in relation to being scared to have certain attacks on Bitcoin. We're going to see we can actually go to the next slide where we see how many transactions have happened in Bitcoin in the last few years. And you see in the beginning where this was sort of the middle here between 2010 and 2011, there were almost no transactions. Almost nobody was using it. This is the transactions per block. So you had less than like 5 or so transactions in average per block. Now, if you have only 5 transactions per block, then your block is only about a kilobyte or 2 kilobyte large. At that time, it would have been very easy for somebody to attack the Bitcoin network by creating huge blocks and by spamming the network with transactions, overwhelming these nodes with transactions and just crashing them, or cutting them off from the Bitcoin network. And that's something that the developers at the time were very afraid about, because it would harm their little project at a very vulnerable stage. But sort of what happened here in the beginning, so we can see the spike up here. Wired published an article about how easy it is to buy drugs online with Bitcoin, or how safe it is rather. And then nobody was using it before. It was kind of an article that just, well, it should have read, this is how it could be, and instead it pretended people are already doing it, but nobody noticed, and people actually started to use it in one way or the other. Again, beginning of 2012, I don't know exactly really what happened. Why did it suddenly become so much more useful? But by that metric, Bitcoin has grown quite steadily. You can see a few of the famous bumps, for example, when Bitcoin price spiked to 1,000 US dollars. You can see that spike here a little bit, right before 2014. But it's not really having a huge impact on the way that Bitcoin is being adopted. And if you look at 2014, when the price was mostly falling, the adoption actually has gone very steadily up. But we have reached the limits. The limits, depending on what kind of transactions we have, are probably here between 1,000 and 1,500 transactions on average. And what are we going to do now, right? And so there's a lot of things that I want to point out, things that Bitcoin could develop. A lot of these things would mean that Bitcoin would develop in a very different way than maybe some of us want to, or some of us believe to. If you can go to the next slide. The number one solution is, of course, the most obvious one. If we have an arbitrary limit on how big a block can be, maybe we should just take that limit out. And what Bitcoin XT, that's what it's called, this proposal, you can also refer to it as BIP 101. BIP 101 is more of a more theoretical framework on how to increase this block size, while XT is a software implementation. And what XT proposes is it increases the blocks to 20 megabytes instead of 1 by next year, and then doubles this number every 2 years. No, it increases it to 8 megabyte, and then doubles that 10 times, so that within 20 years you have 8 gigabyte blocks. And 8 gigabyte blocks, that can compete with things like PayPal or things like Visa. So by the year 2035, Bitcoin would then have scaled up actually to something that is quite large. But there's also lots of concern around that. Another solution would be, instead of having larger blocks, you would have more blocks. So not every 10 minutes you would choose somebody, but you would choose somebody every minute, which would make effectively, even if a block is still 1 megabyte, you have 10 times the transaction capacity. The idea around that is that right now, a Bitcoin block needs to be propagated very fast. Like you saw, 12 seconds. That's really the maximum of how long it should take. But then in the next, so you have, within 10 seconds, you have a big load on the network. Everybody tries to download the blocks from each other. Everybody tries to push these blocks and verify them. But then for 10 minutes, nothing really happens, and the network sort of stays idle and just listens into transactions. What more blocks would solve is that it would turn these big spikes into more of a constant stream. And very interesting, more from a research perspective, incredibly interesting solution is Bitcoin NG, which proposes to completely remove the transactions from the block. And you publish a block by just publishing the header. And that block appoints you choose a private key for this block. And every transaction in the next 10 minutes that happens is going to be signed by you, right? That also turns those big spikes of receiving a block into more of a constant stream of transactions, and people say that has a less of a load on the network and that has less of a load on your computer. One solution as well is sidechains. You say you have Bitcoin as this incredibly trusted core blockchain and big transactions around it. Lightning Network, for example, and it's not exactly a sidechain, but it could also be regarded as that. So it's a protocol that makes use of traditional Bitcoin transactions, except that they're not cleared out. They're just being sent as unpublished transactions to each other. Complicated white paper. Essentially, it would allow you to make very quick transactions between lots of users, and at the end of the day, you receive that one Bitcoin transaction that you can have, or at the end of the month, things like this. In the same way that most people today interact with PayPal. PayPal can have a big load of transactions that are relatively low cost, but then people take their balance in PayPal at the end of the month and put that into their bank account. You could imagine that analogy to work with Bitcoin as well. And the last one, which is what some people are afraid of the third party, some people are afraid of the bigger blocks. I'm going to explain why that is. Third parties would be a way to say, well, you have some software, you have some parties like Coinbase, or I don't know if you've heard of ChangeTip, who allow you to transact Bitcoins within the users of their system, but they're not actually Bitcoins, they're just Bitcoin-denominated like tokens within their own system. So you load your Octopus card with Bitcoin, and then Octopus payments is getting, or you just make lots of little payments, for example, in stores, and as soon as that card is empty, you just make another single Bitcoin transaction. But most of the transactions are done by a third party, not through the Bitcoin network. And the number one reason why we're having this discussion and why this discussion is so important is because we only really have one way of trying it out. We only have one Bitcoin blockchain, and the way that the economics work is that it is very difficult to fork or to successfully fork, but even in a fork, one of the two chains will very likely die. So the number one metric that people usually apply is what's the value of Bitcoin, and they pin it down to really just decentralization. The only value of it is that it decentralizes that kind of trust. It's not valuable as a payments network because Alipay and PayPal are probably better payment networks because they will always be able to make faster and more transactions per second. Bitcoin never will be. It's also not really as valuable as like digital gold because gold is already gold. No need to have a. You can look at the last slide about decentralization. I hope that makes a little bit of sense. We look at this in a way of looking at both extremes. What would happen if blocks were incredibly small? Like imagine even smaller than 1 megabyte. Imagine you could only make one transaction per 10 minutes on the Bitcoin network. Then everybody could run their own node, right? You could on your phone run your own Bitcoin node, and it would never get full. I mean, the kind of space that we have today on our phones, you would have one app with a few hundred megabytes. It would never get full, and would just listen to all the blocks that are happening and listen to that one transaction, would verify it, and that would, let's hear this one, everyone can run a node, right? So you can really verify all transactions. You can see all transactions that are happening on the Bitcoin network with a device that fits into a light bulb, right? Or a device that fits into your email app, like things that are very tiny. You can verify the protocol, so you can really make sure that there are only 21 million Bitcoins and that the rules haven't been changed. And you have a big voice inside that protocol, because to change that protocol, you would then need to convince all these people who run Bitcoin nodes in their light bulb to change the software. Everybody could have a very low barrier to mining, because you could, as a miner, you still need to run your own node if you really want to verify that you compile this all yourself. So everybody could really mine. It would also be very difficult for a single entity to shut down miners. But you would need nobody could make transactions. If there's only one transaction per minute, then that transaction is probably going to cost like 10 Bitcoin just in transaction fees, because it needs to compete with other transactions that were being included in that block. So if you couldn't ever pay for it, not a single individual would have the ability to make a Bitcoin transaction. a lot of the people who have Bitcoin today, we don't own hundreds of Bitcoins at once, right? So we probably would have such small amounts of Bitcoin we couldn't even easily transact them. We could still use Bitcoin, right? We could still transact with Bitcoin, but we would need to have one of these side chains or one of these Lightning networks or third parties who transact for us, and all we can do is make sure that the Bitcoins that they claim we have are, well, still exist. But you can see that this is a very problematic solution, because even if nobody can change the Bitcoin protocol, and even if anybody can mine, it's still very easy to censor this network again, because you're going to have very few third parties. For example, it might be octopus card payments, who the government could go to, or who would have an interest in, for example, closing down their systems for a competitive advantage, rather a monopolistic advantage. And that would be, right, that would no longer be a centralized system. On the other hand, imagine we really have 8 gigabyte blocks, and every 10 minutes there's this big 8 gigabyte file being sent through the internet. Then we in this room, we probably couldn't run a Bitcoin node either, because just paying for that kind of bandwidth and having a data center that can process it costs quite a long time to process all these transactions to verify them. In the next step to just store the blockchain, imagine how many hard drives you would need. So again, everybody could have then a Bitcoin private and public key. Everybody could make transactions, because you don't need to run a full node to make transactions. You could just have your little apps. But you could verify yourself. You could verify this is the Bitcoins I own. You can digitally prove that you own these Bitcoins. Nobody can trick you into censoring these, into taking away your funds. But you cannot verify the protocol. So you have no way of telling, are there still only 21 million Bitcoins? Maybe it has been increased to 50 million Bitcoins. Or maybe some entity has changed the protocol in a way that they're allowed to themselves just add 1,000 Bitcoins out of nowhere. And that's also a bad solution, right? It's also a case where Bitcoin is no longer decentralized, because there are going to be very few parties in the world who are going to be able to run these Bitcoin nodes in their data centers. And again, somebody who wants to control, somebody who wants to take away your funds, they would not be able to really steal your Bitcoins, but they would be able to censor your transactions. They would be, because they control these nodes, right? So any transaction that comes from a certain address, they could simply refuse to put into blocks. So you can imagine that in the way companies that are more going in this direction of big blocks, like you would imagine like the big data center people like Microsoft and Amazon running Bitcoin nodes, and nobody else would, but everybody would be able to make transactions. And in this case, you would imagine everybody runs a node, but only the big guys like PayPal or Coinbase could be able to really make transactions for you. And that's a big divide, right? That's two extremes that are both obviously not decentralized, and they're obviously bad for Bitcoin. But where in between, how far can we move towards bigger blocks without it getting problematic, and how far can we move to smaller blocks without it getting problematic? And for that, unfortunately, we do not have a clear answer. And to solve that, we need to do testing. We need to try out different things. We might even need to rebel within Bitcoin. That's what proponents of XT are saying. They're saying, well, the only way we really have to scale this is to try it out with larger blocks. But who knows what kind of effects that is going to be having, right? So expect a very exciting next few months or even years in the Bitcoin protocol before we really figured out how much can we scale it and how much can we, and what can we do on top of it. And I hope I didn't take too much time. Who wants to speak next? Did you figure it out between each other?
Why don't I go, since we're already connected?